All right, I guess we'll go ahead and get started. Got a couple of people in here. So welcome everyone. This is a quick live stream on state compression, more specifically compressed NFTs on Solana. So we'll go through this PowerPoint here, talk about some of the high level things, and then we'll dive into some actual code. The code we're going to go through, I'll link it up in the chat. It's a GitHub repo that is live on the Solana Developers page, and it's basically a proof of concept that goes through minting compressed NFTs on top of with TypeScript. Got too many tabs open. There we go. So we're just going to go through the actual TypeScript code within here, walk through it, kind of explain some of the different portions of how Merkle Trees work for one, concurrent Merkle Trees, which is like the special sauce of compressed NFTs and state compression on Solana, and we'll talk about some of the pitfalls and composability constraints that you might find yourself running into. So yeah, let's go ahead and get to it. So like I said, we're going to talk about specifically with our code. We're going to go through minting, reading, and transferring compressed NFTs. So how state compression kind of came about on Solana is relatively, it's pretty expensive to actually create NFTs on Solana. It costs about 0.012 Sol per NFT. And at small scales, if you're doing smaller collections, couple hundred, couple thousand, that's not really the biggest deal. But once you start hitting larger scale, where you're trying to think about having million size NFT collections, or you have larger businesses that are maybe trying to integrate blockchain and Web3 technology, having this large cost that does kind of exist within their broader potential NFT collection, those costs add up really, really quickly. So the amazing devs at Solana Labs and Metaplex, they've been working on this really awesome thing called state compression. So one of the key point about state compression is that it actually takes the cost of minting NFTs on Solana, it reduces it drastically. So we've got this little chart here, and in the middle, in this this purple column, you can see some data points on approximate cost in Sol to actually mint compressed NFTs. So if you were to create a 100,000 NFT collection on Solana today with non-compressed or uncompressed NFTs, that's about 1,200 Sol. That's a pretty hefty chunk. With compressed NFTs, you can get that down to about 4 Sol, and there's some caveats on that, and we'll talk about that here in this stream. And then when you get to even larger scale of NFT collections, you can take like a 1 million size NFT collection, and that's 12,000 Sol. That's a lot of Sol with traditional NFTs. But with compressed NFTs, you got about 5.5 Sol, give or take some. And then you can notice that with as these collections get even larger and larger, the cost can be reduced. It's non-linear as you go. So you can get 100 million NFTs for about 56 Sol, 55 Sol. And there's a strong caveat with that, which we'll go through in this stream. All right, so what do you need to know about compressed NFTs? Primarily, there are two on-chain programs or smart contracts, depending on the blockchain you're using. There's two on-chain programs that are handling all the magic sauce that is compressed NFTs. You have the Bubblegum program, which is the Metaplex standard and the actual from the Metaplex program library that's actually used to hold all of the structural information on specifically compressed NFTs within the broader account compression or state compression within Solana. And then the second smart contract that you're going to actually deal with is the account compression smart contract, or the state compression. And this is part of the SPL program library, the Solana program library. And there's two differences between these two. There's two like main segments between these two, where the state compression program is actually what's handling the on-chain concurrent Merkle tree, which is like this magic sauce that Solana has in order to handle all of the Merkle trees and actually storing the information on chain. And then the Bubblegum program itself is actually used to, like I said, it holds all that structural information specifically for compressed NFTs. So you have state compression, which is the generic program on Solana, and then you have your bubblegum, which is specifically for compressed NFTs using state compression. So you might have noticed that one of the things I did say is Merkle Trees. This is a bit of a contention point amongst developers and non-developers that don't really have the strongest understanding of it. And that's, to be fair, that's totally cool. It took me about 3 weeks just to wrap my head around how the Merkle tree works and how concurrent Merkle trees work. And it's really cool. So at a high level, a Merkle tree is just it's a data structure. It's a hash-based data structure where you can take a large amount of information stored in our leaves. That's these green boxes right here. So you can get my mouse to show up. So that's these green boxes right here. This is the actual data. You can think of this in the context of compressed NFTs. This is your actual NFT. This data is, you take your normal standard Metaplex metadata standard for NFTs on Solana. You take that information, you run it through a hashing algorithm, and that information gets stored on chain, right? So you have all these leaves, that's the green. And then each of these leaves get hashed together with their most adjacent leaf, creating a branch. And then each of those branches get hashed together, create a bigger branch, so on and so forth, as you just continually climb the tree until you eventually get to this root node or root leaf. And this actual root is part of the information that's actually stored on chain. And that's what kind of makes this whole compression concept actually work, is we can take all of this off-chain data, and that's because all the compressed NFT metadata and everything, it's all stored off-chain, but it's verifiable using the Solana ledger. So all the information gets sent through the ledger itself and secured by the Solana ledger, so you have the full security and integrity of the Solana blockchain, which is really cool. So that's like at a high level, just like real quick how a Merkle tree works. You don't have to know super in-depth information about how specifically a Merkle tree works in order to use state compression or compressed NFTs on Solana. But having a stronger understanding of it will help clarify a lot of the pitfalls and potential composability issues that you might run into as a developer trying to use this technology. So if I'll take a look here in the chat to see what people are asking. Did I go to blockchain college? No, I did not go to blockchain college. So one of the questions in the chat is compression like zipping them. No. So that's actually a fairly common misconception with state compression on Solana, vice like a traditional, zip archival compression mechanism that you would find within, computers broadly. So using this concept of a Merkle tree, we can compress all the information that's stored within this tree, all this off-chain data, all our NFTs, all the really whatever off-chain data you want. Because it all gets hashed together and those hashes get hashed together as you climb the tree, we're only storing this root hash on chain, which is about 32 bytes. So you can cryptographically verify all this off-chain data while only storing about 32 bytes. And that's like the special sauce of how this all works, how we get this large amount of cost savings. So effectively in the end, you're actually trading Solana account space, which is relatively expensive, for Solana ledger space, which is very cheap. And there's a caveat sort of trade-off with that we'll talk about here in a couple of minutes. Love the idea. So what are the disadvantages? Ooh, that's a good question. We'll talk about some of the disadvantages here basically right now. So like the disadvantage, actually, can you clarify your question about the disadvantage that you're looking for? Like, it looks like it's Ben T. Oh, and we've got the phenomenal Noah Gundotra just joined the chat. He's actually the Solana Labs developer, primarily behind the state compression program. So huge shout out to Noah there. All right, we'll keep going, and then I'll looking for Ben to kind of clarify his question a little bit, or their question a little bit, rather. So, like we're saying, we're storing the actual Merkle root. That's that orange value. Get my mouse to come back. That's that actual orange value. It's the very top of the tree. That's part of the information that we're storing on chain, and all of the leaves are actually stored in the ledger. So you can see just an example of the transaction information that gets sent through the Solana ledger itself. So that's in the instruction data. So it's all the actual bytes that you can see here. visually represented in their hex values or base 58. Can you start the presentation so we can see the font bigger? Oh, I'll post this, the link to this presentation after. Once I try to full screen it, it kind of takes over my whole screen. I have a very large screen, so it kind of like skews the whole thing. Let me see. Let me get the share links, that way everyone can see this. All right. There you go. There's the link inside of the Twitch stream. So that way you can open up the PowerPoint yourself to get a better view of actually seeing what's in here. Take a quick sip of water. So there's another question, again from Buffalo on the beat. Does compression affect the value of the NFT? Would it make their value lower since they're cheaper to mint? Is that logic right? So I think I understand your question. So your question is specifically about, like, if you had a compressed NFT that you were maybe, it was on a marketplace, name your favorite marketplace, would that affect the value, the broad market value of it? Not specifically. To answer your question, is not specifically because of the technology behind it. Whatever your particular NFTs are going to be valued by the market, that's up to the market. The actual technology underneath it doesn't have any play into the value that your NFTs could derive. In fact, from a business or a developer perspective, it costs a lot less overall to actually create a collection. So, like, you can kind of think of it as a net positive for yourself and your NFT holders. Another question. Oh, yeah. Looks like Noah's in the chat answering some questions, so awesome. Thanks, Noah. Apologize if you might be able to hear some of the background noise of my house, I guess. So let's actually talk about how the process to actually use compressed NFTs. It's primarily in 4 steps. So for minting a compressed NFT specifically. So you have to initialize this Merkle tree on chain, and there's both a Rust SDK and a JavaScript TypeScript SDK. And like I said earlier, we're going to go through the TypeScript version. And you use the SDK, has a bunch of helper functions, and it's pretty seamless. It's pretty standard methodology of actually creating these trees, just like sending any other transaction to the Solana blockchain. You compile a list of instructions, and then you're off to the races. And then we can actually mint our NFTs into those trees because the actual data itself is hashed, gets stored in the tree. And then one of the trade-offs of compressed NFTs that we'll talk more about later, and that maybe this will partially answer the question about disadvantages, is because of the way that compressed NFTs work with the data being stored in the ledger itself. It's being secured by the ledger. Well, typically you're going to see is RPC providers are going to have indexing services, and I guess in theory non-RPC providers could also have indexing services as well. But we're going to use indexing services to actually read the NFT data, to actually get all of this, like, quote unquote off-chain data that's like secured by the ledger, because the way that Solana is kind of structured is all the information, because it's a state machine. All the current state is stored, and that's like the account information, the account values that we're like storing on chain. But the ledger data is actually the validators, as they're processing transactions, don't retain a very long history of that. So that's why we use things like indexing services from RPCs to actually be able to return that data to us. And Metaplex and a lot of the teams around compression, state compression and compressed NFTs, they built this really awesome thing called the Read API, which we're going to dive into. And it makes both working with compressed NFTs way easier and uncompressed NFTs. So like traditional NFTs on Solana, you can use this Read API basically like a REST endpoint to actually get all the information about NFTs that you want. It's pretty great. And then at the end of that is, once you actually want to change the data of your NFT, your compressed NFT, and that could be transferring ownership to a new owner, that could be actually updating the metadata itself, you have to use what's called a proof of the Merkle tree to actually transfer the NFT. And we'll get into that once we actually get to that portion. take a look at the chat again. And yeah, so someone asked, can this compression technology be used only for NFTs? The answer is flat out no. Compressed NFTs are the primary use case right now. It's kind of like the first example of how to use state compression. But there's a lot of protocols and projects that are coming online that are using state compression in different aspects. And so you can use it for anything you want. You just need kind of like the extra infrastructure around it. All right. So as far as initializing a tree goes, like I said, there's going to be a couple of caveats that you need to think about. And these specific caveats are these specific values for creating your tree, your like size values, if you were. There's 3 values, and each of these 3 values are going to determine how the overall cost of creating your tree, how many compressed NFTs you can store in your tree, and then how many how composable your tree and your NFT collection can be. And we'll talk more in depth about these once we actually get to the code. But the 3 values are your depth, your buffer size, your canopy height or canopy depth. And your depth kind of determines the capacity of your tree. So how many compressed NFTs you can store in it. Simple calculation, just 2 raised to the power of the depth. So if you wanted to create a tree of size, or a depth of 3, so 2 to the power of 3, that's going to be your capacity. And I'm not sure if I mentioned this at the beginning, but concurrent Merkle trees and Merkle trees, it's a perfectly balanced binary tree. So it's always going to be 2 to the power of whatever your depth is. And then we have this buffer size value, which you can kind of think of the buffer size as, and this is kind of like one of the things with concurrent Merkle trees, this special sauce that Solana has, is that with a high throughput application like Solana, a traditional Merkle tree, it doesn't really work, because in order to change any of the information, you need to use this whole proof thing. We'll talk about it more later. So you're kind of limited to how many changes you can have within a certain block. So realistically, a traditional Merkle tree, you have 1 change per block because you have to validate the entire proof every change. But with this special sauce of concurrent Merkle trees, you have basically, we can take this information and we can store it on chain. That's part of the canopy as well, a little bit. But we store part of this information on on chain itself. So that way we can actually have up to the max buffer size of that many changes per block. So it adds this massive amount of concurrency that a traditional Merkle tree just doesn't have. And then the last size value is the canopy height itself, or canopy depth. This is, I'll go more in depth on this later, but basically this is going to determine what portion of your Merkle tree proof is going to be stored on chain, which in turn is going to result in how much proof information, how much proof like accounts almost, how much of this extra information you're going to have to send with every single transaction you do within using compressed NFTs or state compression overall. So we'll go more in depth on the canopy height, because the canopy height is going to be one of the primary drivers of cost that you can kind of almost choose your own adventure of selecting your primary cost versus your composability that you want your collection to actually have. All right, and then we'll go through actually minting an NFT. So let's go ahead and do that. Check last minute before there's any questions. Looks like Noah's being the real MVP over there about answering a bunch of questions. All right, so I'm going to transfer over to VS Code. All right. All right, so I'm in VS Code now, my preferred code editor of choice. Use whatever you want. And this is just, like I said, this is that repo that I gave the link to in the chat. And I will link it up again just in case anyone's joining and didn't get it. Can you guys, can everyone in the chat let me know if they can actually see the actual text? I can make it a little bit bigger too. Make it a little bit easier to see. Text looks good. All right. So within this repo, there's a README that kind of explains how to actually set up this repo and how to use it locally. So if you wanna clone it, you can do that. Kind of explains some of the scripts that are included and some of the broader setup for this. But if you are either following along on the code repo itself, or if you're just watching the stream, then we're gonna first look at this verbose create and mint script within the scripts folder. Like I said, this is all a TypeScript project, and we'll go through actually running these scripts as well, and we'll mint some live. In fact, I am going to delete this keys folder I have. All right, so check the chat. Okay, so at the top of this TypeScript, and if you're not a TypeScript developer, if you're just JavaScript, then it's pretty similar. Also, if you don't know TypeScript, you should check it out. TypeScript is very cool. So we have some of our standard imports here at the top. We're loading in Solana Web3.js. We're loading in some local helper files or helper functions within this repo itself, and we'll walk through these just very briefly when they come up to explain what they're actually doing. A lot of these helper functions are all helper functions. They're just to help locally load key files on my local system or your local system if you're running this locally. Said local a lot. And then we have this account compression SDK, and then we have the Bubblegum SDK and SPL token metadata. And in this case, this is just a type from this package itself. And then we've got these helper functions, again, within this repo, and this wrapper connection, which this is a very special thing within this repo. It just kind of makes the overall interacting with the indexers a lot easier. So we will explain that when we get to it. And so one of the things that, like I mentioned, actually, I'll get to that in a moment. So some pretty standard boilerplate at the top where I'm loading in my environment variables, and then I'm actually loading in and creating a couple of wallets, local test wallets, using these local helper functions within this repo. I'm either loading or generating a test wallet, and I'm calling it test wallet. Same thing with this payer, because I'll go ahead and open up my terminal as well. I'll show you that I am, in fact, on DevNet, and the address that I'm actually using for all of this, because this address is going to be the payer. It's this Nick address, this vanity address, and this address does, in fact, have DevNet Sol. So my balance is about 52. So we're loading in these key pairs, and then I'm actually saving the key pairs to this local file using this helper function, and that just makes it so you can kind of do a lot more testing a lot easier. All this information is kind of documented within the README as well. And then we're actually going to make our connection to the RPC similar to how you normally would. I've got my RPC URL stored within an environment variable, and then I'm creating a new connection to using Web3.js using this local wrapper connection. So I got to open this up. All right. Check the chat real quick. Take a sip of water. All right. So this wrapper connection is just an extension class on top of the normal Web3.js connection. And basically all this is doing is it's making it so I'm adding these extra RPC endpoints that I'll talk about in a couple of minutes. And it's basically just making very simple post request using the JavaScript fetch API. So we're just making a post request to my RPC URL. And when you're dealing with compressed NFTs, like I mentioned at the beginning, we need these indexing services generally provided by some of your favorite RPC providers. So right now you've got Helios is one of those providers, Triton, Simple Hash, and I believe Genesis Go also supports it. Maybe Noah, you could back me up in the chat if Genesis Go supports the Read API yet. But a lot more providers are coming online to actually support this Read API. And the special thing about this Read API is it gives a couple of methods that are additional RPC methods on top of the normal Solana RPC methods. And that's what this helper class is doing, this wrapper connection. It's making it just a convenient typed interface for my local repo. And we've got get asset proof, get assets by group, and get assets by owner in here. And we'll talk more about those when we actually start reading and using this wrapper class and these special functions. But yeah, so inside of my local environment variables, I have a RPC provider that actually does support this read API. So that's a very important thing to understand and that you correctly do. So if you don't already, you can go and sign up for like dev accounts for those providers if they support that. And then we're actually going to log out. We're going to get and log our starting balance because compressed NFTs are super, super cheap, right? Especially compared to traditional non-compressed NFTs. And then so we'll log that out, and then we'll at the very end of the script we'll show the total balance change to show that it's insanely cheap, drastically cheaper than before. All right, so now we get into the real meat and potatoes of it. We can actually start defining the information to actually create our Merkle tree on chain. So we need to create our max depth, buffer size, and canopy depth that we're going to use within creating our tree, like we talked about earlier. So in this case, I'm setting a max depth of 14, which 2 to the power of 14 gives us about 16,000 nodes. And we can set these values to almost anything you want. If you're using TypeScript, you can check out the type, and there's these max depth and buffer size values that are already kind of like preloaded and pre-staged within the account compression SDK. And now it's super important to understand that these are the only values that you can use within using compressed NFTs and state compression broadly, because these values are also like hard coded into the smart contract itself, into the program on chain. And yeah, so you need to make sure you're using one of these like combinations. So actually, in this case, we'll mint a even larger collection. We'll do 1 million NFTs because I have about 50 SOL in this account, so I have more than enough to mint. So we'll mint 1 million NFTs as part of this collection, or at least we'll size our collection, our tree, to support 1 million NFTs. We'll only mint a couple because time. So yeah, so we're setting that max depth, and like we said, the max depth determines how many nodes, how many leaf nodes you can actually put inside of your tree. Our max buffer size is that concurrency level, so you can kind of think of it as how many changes your tree can support within one block. That's kind of how you can think about it. And then we have this canopy depth. We kind of talked about the canopy depth earlier a little bit, for those of you who have been around since the very beginning. And in this case, I'm actually just setting this to max depth -5. So your max depth or your canopy is going to be limited to about 19 or 20-ish, because you still have to maintain within the 10K account limit size that Solana has. So that is a like restriction that you have, I guess. But in this case, I'm setting it to max depth -5. And we'll talk about why this is important later when we go to actually transfer our NFTs. Because your canopy depth is going to determine how much extra like proof information, how big your proof is that you have to send with every single change transaction. So if you're transferring NFT, if you are updating your NFT's metadata, you have to provide this proof every single time. You don't have to when you're minting, which is more convenient, I guess, but you still have to do it anytime you're changing. So we're setting it to max depth -5. So in this case, we're setting it to 15. So this value is going to determine broadly like how much our tree is going to cost. And that's this next chunk of code here in this repo is I'm actually just getting the total space that's required for the tree. And we're going to get the total LAMP ports, do some math, and actually print that out. And in this case, I'm going to throw a quick return in here. So that way, if I can actually type, and that way I can actually run this so we don't go anywhere, just to demonstrate the different estimated costs for actually creating these trees. So like I said, this tree can support more than 1 million nodes in it. And so we'll go ahead and run this script locally to show how much it's actually going to change. And that's the verbose script. And once this actually makes the connection with the RPC, and assuming the DevNet gods are going to be kind with us today, because it's always a struggle when you're doing live things. All right, there we go. So you can see we have the same payer address that I demonstrated earlier. That's locally on my file system. In this case, we actually generated a brand new test wallet address, and that's now stored inside of this local keys folder with those helper functions I talked about. And you can see how much space it actually takes and the estimated cost to create this tree on chain. And that's because we have a max depth of 20 and a canopy depth of 15. So that's 2 million bytes, a little bit more than 2 million bytes to actually allocate on chain. And we're going to pay about 15 Sol for that. And total, we can store about 1 million compressed NFTs in this tree. So that's super cool, right? And just as another demonstration, we'll go back to this initial size, and then we will let that run to actually see the different cost. And I'll change this back because we're going to create a 1 million size. All right, so I'll go ahead and remove this return as well, and we'll continue on letting this run in the background. Okay, so next, looks like it finished. So to create this much smaller tree size, it's about 64,000 bytes and 0.45 Sol, give or take, with the ability to hold about 16,000 compressed NFTs within the tree itself. So you can see that it does change quite a bit, and you can kind of play around with your canopy depth and your max depth as needed. So like the thing to think about, or the thing to keep in mind with your max depth, is because you can have multiple trees as part of a single NFT collection, and the typical metadata or the typical Metaplex collection is exactly the same within compressed NFTs. It still follows the same Metaplex standard, but a tree is not the same thing as a collection. So you could have multiple trees as part of the same collection. In fact, generally that's actually recommended if you're doing a really large collection. Say you want to do a 1 million NFT collection. It's probably a better idea to have a bunch of smaller trees in order to make it so your collection can hold 1 million NFTs. So you could have, 10 of these size trees to be able to hold, 10 give or take, of depth of 15, and it's going to help with the composability later, and that's partially due to this canopy depth and how much proof information you have to send. So and we'll talk, like I said, we'll talk more about canopy depth when we get there. Okay. Okay, so now next we can actually get into creating our tree, and I have this helper function set up just for ease of use. So I'll go ahead and open that. And if you're looking at the repo itself, that's within the utils/compression.ts file, and it's called create tree. Pretty self-explanatory. We're taking in our parameters of our connection, our payer, tree, key pair, and that's just a new randomly generated key pair that we're generating using the JavaScript SDK, the web3.js. And then we're going to actually start doing some code. So we're going to derive a tree authority that's owned by the Bubblegum program, because Bubblegum is the standard for compressed NFTs. We actually have to make it so the Bubblegum program has the authority over our tree to be able to support minting new NFTs and transferring ownership and updating the metadata within our tree itself. Because like we talked about at the beginning, the state compression program is different from the Metaplex program, the Bubblegum program. Bubblegum's a additional layer on top of compression. So we're going to derive that address using the SDK, the web3.js, and then we're going to allocate that space on chain using this create Alloc tree instruction. And this is coming from the account compression, SPL account compression program, the SDK. And basically all this is doing is, we can open it up to look at it, where it's just calculating how much space we have needed, that we actually need for the tree itself, just like we demonstrated, just to demonstrate the cost. And then it's just going to create an account that's owned by the system program, using that amount of LAM ports to actually get that, make this account rent exempt. And that's just to actually, and that's like the bulk of your cost with compressed NFTs. Back correct file. That's like the bulk of your cost with compressed NFTs. It's the actual tree creation, and you're going to pay that up front. So with traditional NFTs, if you're doing like a large mint or something, the minters are going to pay for that price, that like account space, that 0.012 sol per NFT. The minters are going to pay for that. With compressed NFTs, the creator of the tree is going to pay for that fee up front, that cost up front. And that's just because you're allocating space ahead of time. And that's just because of how the Merkle Trees and the state compression program works. Like, you have to allocate it up front. So once we allocate our tree, and this is just creating the instruction, we're going to create a new instruction to actually create our tree on chain. And we're passing in some of the standard addresses you might expect. We've got our payer. We've got the tree creator, which in my case, I'm just setting to the payer. If you want to set it to like another address, you absolutely could. This tree authority PDA that we derived above, again, owned by the Bubblegum program. And then we're actually giving our Merkle tree address. So this is the tree key pair that we generated. And then we generated ahead of time, so it's easier to actually send to the different portions of our scripts. And then we're giving the compression program and the log wrapper program. These values are stored within the account compression SDK. And the account compression program, just the address for the account compression. And this SPL no-op, this is part of like the magic sauce of how the state compression works. It's like, you can kind of think of it as like an extra, it's like a helper program in a way that makes it so all the information that's actually getting secured by the ledger, it gets kind of like sent as a CPI call to this no-op program. So that way all the CPI information actually gets stored and secured by the ledger instead of in traditional logs, program logs, because RPCs and validators don't actually like cache and store the program logs. It's like the first thing to fall off because it's frankly less important. But by sending all of this cached information using a CPI call, we're making that CPI call to the no-op program to actually be able to secure that information on the ledger. Okay, and next we're providing in our buffer size and our max depth that we defined before. And in my case, I'm setting a tree to false, or the public to false, because if you set it to true, then anyone could be able to kind of update your tree and mint into the tree. And that's not what we want since we're creating an NFT collection. And then finally, we set the program as the Bubblegum program. We're going to take those two instructions, put them all together in a transaction, sign them, send them to the cluster. Again, in my case, I'm on DevNet, and that's pretty standard. And then we're going to log them out, a convenient Explorer URL, and then we're going to return the tree authority, tree address, which we already had most of that information in the case of our script here. But yeah, and then I'm going to actually save those locally within my repo just for ease of use later for some of the other scripts. All right. So I'll take a brief pause, take a look at this chat. Take a good sip of coffee too. It's black coffee, in case anyone's wondering. It's nothing in here, just black coffee goodness. All right. Okay, I don't see any direct questions that haven't already been answered. All right, so next we're actually going to create our NFT collection. Now, like I mentioned earlier, the process to create a compressed NFT collection is exactly the same. You're using the same Metaplex standard. It's still like an NFT. You still have to create the collection, mint an NFT into it, store the actual NFT metadata on chain. So there's nothing special about compression right here for our collection itself, because the collection is it's just that convenient grouping of NFTs. It makes it so when you're looking at your NFTs, or if anyone is looking at your NFT collection, your NFTs on their wallet, the explorers, it just groups them together. It makes it nice and convenient. It's the exact same thing with compressed NFTs. So I'm defining all of my metadata information, standard information, won't get into it. Have a URI set. It's not a real URL. But then we're actually going to create the tree using this helper function instead of using the method that some of you might be used to, using the Metaplex SDK. I'm just doing it manually just for the sake of having everything locally within this repo. So using the SPL account program or the SPL token program, we're going to create a mint, give it our payer address as the authorities over it. We're going to create a token for it. We're going to mint a single token into our collection, and then we're going to generate our metadata account, and then we're going to actually create the instruction to create that metadata, or to add that metadata onto the blockchain. And in this case, I'm creating a master edition. Kind of semantics, doesn't really matter. You can do whatever type of collection that you want. We're going to create that master edition instruction. We're going to set our size of our collection. In this case, I'm just setting this collection size to 50, just because that's just like a random value I chose. But you can set your collection size to anything you want, and we'll talk more about the actual minting of the compressed NFTs into it once we get there. But we're going to take all those instructions, we're going to put them in a transaction, sign them, send them to the blockchain, and then we're going to log out and explore a URL just for ease of use. So if anyone has this repo like downloaded locally and cloned locally, you can just like run the scripts, and it's going to log everything out very conveniently. So if you're doing a whole bunch of testing, it just kind of makes it a little bit easier. And then finally, after we create our collection, I'm just storing the mint metadata account, so that like associated token account, the master edition account address. I'm just storing all those locally within my repo here, or within my file system here, and that's this list local keys directory that will be created automatically. All right. So this is one of the things that I mentioned earlier, is that an NFT collection is not the same thing as a tree. And there's kind of like a little explainer here that kind of goes over it. And it's like I said, like you can have multiple trees within a single collection. I guess also in theory, you could have multiple collections within one tree, but I would probably strive away from that. That's like, I would consider that an anti-pattern. But you can use multiple Merkle trees, the state compression trees. You can use multiple of these trees to store any number of NFTs up to the limit of that tree, and then you can put all of those trees as part of the same collection, no problem. In fact, that's probably recommended for a lot of cases. If you have a smaller tree, it's more composable. Okay, and now we're going to actually define our metadata for our NFTs that we're going to mint. And one of the beautiful things about compressed NFTs is that compressed NFTs follow the exact same metadata standard on Solana, the Metaplex standard that you're already used to for uncompressed NFTs. Same information using our metadata args type here. Using the type, and we're setting in all of our local information. In this particular case, I am setting the creator's array just because I'm setting it to the payer, who's that Nick account that I showed earlier, and then this test wallet, which is that randomly generated wallet. You don't have to do this. I just happen to be doing it for this example. And then these values here at the bottom, the program version and the token standard, I'm just pulling these in from the bubblegum package, and that's just saying, hey, this is, the program's the original program, and the token standard is non-fungible because we're creating NFTs. So next we can actually get to this helper function, and we're calling it twice. And with this helper function, we're going to actually go through the process of actually minting our compressed NFTs. And for this case, I'm minting 2 compressed NFTs to the same collection and using the same tree. And these are the addresses that we saw earlier. The first one I am sending to the payer account, and the second one I'm sending to the test wallet. So it's actually going to mint. It's going to do it as 2 separate transactions. You could, in theory, do them as the same transaction as long as you're within your transaction size limits. And so that's just up to you to kind of, build that in if you so desire. But yeah, so we're going to mint 2. So the second one is kind of like to simulate an airdrop. So if you were to airdrop to an additional wallet that maybe your Dialect, and Dialect is airdropping a bunch of sticker packs, sticker pack NFTs. This is kind of like the way that you would do it, right? All right, so let's go ahead and open up this mint compressed NFT function. Again, stored locally within the same file, the compression.ts. We're passing in those addresses, the tree address, the collection information. Pretty standard stuff if you're going to actually make an NFT, especially if you're not using the Metaplex SDK, if you're kind of like just doing it yourself and kind of doing it, handling it manually. we're passing in the metadata itself and then the receiver address. Okay, let's do it. And we're going to derive our tree authority again. Same thing as before. It's the tree authority that we're used for our tree that we created our tree with. So it's the using our tree address as the seed, and it's owned by the bubblegum program. And then we're going to derive this bubblegum signer. So, and you can see the bumps are underscore because we don't care about them. We're not using them, and that just makes VS Code a little bit happier. So we're going to generate this, or we're going to derive this bubblegum signer account. It's a PDA that's going to be owned by our bubblegum program, and it specifically has a seed of collection underscore CPI. Now this string seed is hard coded into the bubblegum program. So if you mistype this or you don't include this or don't do it correctly, bubblegum will not be able to actually sign the transaction and like the CPI call in order to actually update your Merkle tree on chain. So your transaction will fail. Your mint transaction will actually fail. And you'll be able to like look at your logs and figure out what happened. But it's very important that this is correctly spelled, all lowercase. And if you want to look through the bubblegum Rust code, you'll see this value and a couple of other values that are hard coded in. Okay, and now that we have our signer PDA derived, we're going to use this helper function that comes from the bubblegum SDK, the JavaScript SDK in our case, and this is going to make it so we can easily create an instruction for actually minting to our collection. Since we have created our collection ahead of time, we can actually mint to it. All right, so we're passing in a lot of standard information that you might have guessed if you've been around the Solana block, no pun intended. We've got our payer, we've got some authority, some delegates, we've got our collection addresses, and then some extra program IDs. Because if you're unfamiliar with how instructions and transactions work on Solana, basically because of how the runtime is structured and how it works, you have to provide every single address that you are interacting with, whether you're reading or writing to. And so we have to pass all of those addresses in our instruction. And that's exactly what we're doing. So the Merkle tree address is just the tree address that we generated at the beginning, and the tree authority that we generated, or that we derived as well, same one, owned by the bubblegum program that we actually minted our tree with. And then we have this tree delegate, leaf owner, and leaf delegate. So the tree delegate is just a delegated authority if you want to or need to, depending on what you're using your tree for. If you need to delegate authority over your tree, then you can do that. In my case, I'm just setting it to the payer, who is in this case, the actual creator of the tree. But you could set that to whatever address you need to for whatever application you're doing. And then we've got our leaf owner. The leaf owner is the actual address that's going to receive our compressed NFT. In this case, I'm setting it to the receiver address if I supplied it with this helper function, and if not, then the payer. So with the example of our verbose create and mint script, we're sending to our payer and then our test wallet. And then we have the leaf delegate. The leaf delegate, in my case, I'm just setting to the payer for the transaction. You can set this to whatever you want. You will have you will have to actually include a value for this. So if you are trying to delegate access or delegate authority of a particular leaf, so delegate authority over an NFT, you have to set this value. If you do not need or do not want to delegate authority, just set it to the receiver's address, because you still have to set a value for it, right? So those are your options for that, I guess. And there's kind of like a little bit of a note here. We're just setting it to the payer, which is actually going to help locally within this repo. It's going to help with some of the testing, just to demonstrate some of the errors that you might see. And then we're sending in the collection information, the authority, mint, metadata, master edition, so on and so forth. Standard stuff if you've ever dealt with NFT collections on Solana. Looking at the chat, someone asked something about programmable NFTs, and I see Solana Jonas, also from the Foundation DevRel team. Programmable NFTs are not yet supported within compressed NFTs. Okay, so then the last bit here, we're sending in our programs that we're interacting with and our bubblegum signer. Again, our account compression, the SPL no-op, bubblegum signer, and token metadata. Those are our standard programs that you're going to use for all of your bubblegum instructions. And then we're actually sending our metadata information that we created, and then we can take our instructions and put them in a transaction, sign them, send them to the blockchain. And again, we're going to log out the URL again. Okay, so that is actually pretty much the end of this verbose create and mint script. And then at the very end, we're just going to get the updated balance and then log that out to the console just to show the actual cost of what it takes to both to do the entire process, like end-to-end solution of create a collection, create a tree. In this case, don't remember the value I have set for it. To 130,000. So we're going to create the tree, create the collection, and then we're going to mint 2 compressed NFTs, all within this script. It's going to handle those multiple transactions. If you're, in production or doing anything that's not just command line scripting, then you could make it more efficient and have less transactions pending your transaction size limits. Okay, so let's go ahead and run this. I'll go ahead and clear my console. And we'll go ahead and run this script again and give it a couple of seconds, and hopefully DevNet wants to play nice with us. If you're also poking around within this repo, there's another create and mint script in there. It's basically the same script. This verbose one has additional logging just for ease of use and ease of understanding, has extra comments in it to kind of explain what's going on. But functionally, it's the exact same. So you can see here at the top, we're estimating about 2 SOL in order to actually mint our tree and allocate space for that tree. And this particular tree can hold about 130,000 nodes or compressed NFTs within this one tree itself. So we've successfully created our tree. We have an Explorer address here. In fact, I'll go ahead and copy it, and I'll put it into the Explorer if anyone wants to look at it. Oh, didn't quite copy it for me. Well, doesn't seem to want to copy for me. But the tree address is in there. You can open it on Explorer to actually view the transaction as well. There we go. Yeah, so it looks like our script completed successfully. DevNet was kind to us today. And so we've successfully created our tree. We have created our mint account, metadata account, so on and so forth. And then we have successfully minted 2 compressed NFTs, all for the total cost of 2.09 SOL. And we could still continue to mint NFTs over and over into our tree until eventually that tree tops out. And then if you wanted, provided your collection is set up to support that many, like we talked about earlier, this one is only for 50 SOL or 50 NFTs in it. But if your collection is set up properly, you can just keep minting until your tree maxes out at the total number of nodes, and then you could create a new tree and continue minting compressed NFTs to it to your heart's content. And that is one of the beautiful things. It looks like there's a question. If I only want a 10K NFT collection, it'd be the same thing. You could, to answer the question, you can create a collection of any size you want. And you can use any size of tree you want. It's just what cost you want to have for actually creating that tree. If you wanted to create a 10K NFT, you would need to set a max depth of 14 because you have a max number of nodes of 16,000. So you have to have less NFTs than the max depth supports. You can always be under, you cannot go over. And once you actually create your tree on chain, you can't change any of these values. You can always create another tree, though. All right. Okay, so next we will go into... I have there's an extra function inside of here, or an extra script inside of here that will also mint additional NFTs into the same addresses, the payer and test wallet. So if you look at the repo, then you can kind of play around with that if you so desire. All right. So next is the again, if you're within the repo, next is we're going to go through the fetch NFTs by collection, because we created one collection, and this script is this portion we're going to actually talk about the read API and how the Metaplex read API that is supported by these indexers, how that's going to play in all this. It's going to be the primer on that. So within this script, we're taking in the same wrapper connection that I mentioned earlier. We'll talk more about it again here. Some helper functions, and then the standard, some standard functions within Solana Web3.js. I'm going to read in my environment variables, and then I'm going to use the helper functions to actually just locally load all these key pairs. So if I open up this address or this file here, these are all just the random addresses that were generated for running the verbose script earlier, and it just makes it so I can more easily use them within this repo. So we're going to load them, just do some quick validation to make sure that we got our collection mint address, and then we're going to actually use the Metaplex read API that's provided by our indexers. The support is provided via the indexers that do support it. Like I mentioned at the earlier part of the stream, the read API is only supported by a couple of indexers right now and RPC providers. That's Helios, Triton, Simple Hash. I'm pretty sure Genesis Go. I'm not sure if I was corrected on that in the chat, but more providers are coming online soon. All right. So the read API. So the special sauce that the read API is it's basically another name is the digital asset standard read API, and in a nutshell, it's like you can think of it as like an RPC extension where the read API and RPC providers that support it adds extra endpoints, just like any other endpoint that you're already used to on Solana. It adds these extra endpoints that we can use specifically for compressed NFTs. And one of those, and I'll pull up this wrapper connection class here. Excuse me. We'll go through this first one, which is get assets by group. And in fact, I will, in the stream notes or the stream chat, I'll give another link. That's the playground for the read API, so that way you can kind of play around, see what the overall like schema is for information that's supported. You can kind of play around with it if you want, if you don't already have a RPC provider that supports it. And this get assets by group RPC method that is within the read API, it's going to take in a couple of values, and then we're just going to make a post request to the RPC that uses this method name, get assets by group. We're going to send it a group key and a group value, and then close out some of these. And then it's going to return whatever information it returns. So get assets by group, primarily the one group key that is supported right now is a collection. So your collection is a group of NFTs, so that kind of makes sense. Eventually more types of groupings will be supported, but currently there's just collection. So we're going to say, hey, we want to get our collection, all the NFTs that are part of our collection. In this case, it's from our collection mint. So far we've minted 2 compressed NFTs to this collection. And then we're just going to like log that out to the console. And there's nothing like super special about that, specifically about like the logging, but the information that gets returned with each of these, within each of these RPC methods, these read API methods, there's a whole bunch of information, and you can look on the playground and look at the actual RPC spec for it. There's a ton of information that gets provided by these indexers, and this is true for both compressed NFTs and non-compressed NFTs, uncompressed NFTs. Ton of information. So you can use this read API, even if for some reason you don't want to use compressed NFTs, which would be foolish, you can use this read API to actually get all of that information. So we'll go ahead and just log the entire asset that gets returned. And if you have this this local repo, you can see the type file that's within here and kind of look at the schema a little bit. But we'll go ahead and run this. So we're going to fetch by the collection. We'll go ahead and run that. And we'll see the information that gets returned to us. All right, so you can see that there's a whole bunch of information that gets just thrown into the console here because, and you can kind of scroll through it, scroll to the top. There's a little bit of, helper formatting, if you will. And you can see that we have 2 assets were returned from the read API for our specific collection because we've only minted 2 NFTs to our collection. So we're just printing out all the information that gets returned. And you can see super quickly that it's a version 1 NFT. We have our JSON URI that we set when we actually minted our NFT, the basic metadata. One of the cool things about the read API is that it will automatically fetch the JSON URI, and then it's going to load it into the metadata, the content metadata object field. So this is the only information that was stored within our NFT itself. It'll try to auto fetch that URI. In our case, it doesn't exist, so it doesn't put any other information in it. And then we have our authority for our NFT itself. And then we have this compression field. And then we have our grouping, since you can see that this is a grouping by collection and our collection address itself. We have the royalty information, the creator's information, and then ownership also is pretty standard. The ownership, you can see that this particular NFT is delegated to this NIC address. The owner is the owner itself. And then if you look at the last one, the owner is the NIC, no delegation. So because we minted one to the payer, which is the NIC address, and then one to the other randomly generated one. So that's why you're seeing a difference there. So let's talk about this compression field. So this compression field is going to be, it does become pretty important when you're working with compressed NFTs, because like we talked at the beginning, your compressed NFTs, when you go to transfer them or update the metadata, you need some of this information, and also some of this information can be helpful to verify that your information is still correct, because like we talked about, the compressed NFT, the primary data is stored off-chain. It just gets secured by the ledger, and it gets served back to us by indexers. Well, you can take part of this information, this compression field, some of the information in here, and you can actually, on your own client side or in your own on-chain program, if you provided it to it, you can do that verification to cryptographically verify that your RPC provider is not doing any funny business, that they are giving you good information. So you can actually do that with that. But you can see here that this is in fact a compressed NFT. It's true. We have a data hash, creator hash, asset hash, and our tree. This tree is the same address that we randomly generated. And then we have this sequence and leaf ID. So we minted 2 NFTs. The first one has a leaf ID of 0, and that's why it shows up last, because of how we're sorting. And then the second one has a leaf ID of 1. Every NFT you mint is just going to keep climbing that number, and it's kind of like a nonce number if you think of it that way. And this asset hash. This is a super important piece of information. This asset hash or asset ID, you can kind of think of this like if you think of traditional NFTs on Solana, they all have an address, right? You can kind of think of that as this is the address for your compressed NFT. It's not quite the same. Currently with block explorers, if you try to open this address, it doesn't really show anything, because it's not an account address. It's the asset hash that is stored within that Merkle tree, and the only thing that's stored on chain is the Merkle tree root. So this is not technically stored on chain. That's like easily accessible. And eventually, once explorers start supporting the compressed NFTs more, then I'm sure there'll be some ease of use to be able to actually check for these types of things. But this asset hash is going to be super important, and I'll show you why. So this is just so that's the fetching the different information. There's also another fetch NFTs by owner function, or a helper function in here, or a helper script rather. It's doing basically the same thing. I am going to go ahead and run it though, because it does save some information locally. So we'll go ahead and just run this as well. So while that's running in the background, we're doing a very similar thing. We're getting our assets. We're using this read API RPC method, get assets by owner. We're giving it our owner address of this test wallet, same wallet that we generated with it. And then in this case, it's just going to log out compressed NFT information. There's this quick little check here. If it's not compressed, just return. Keep looping through all the assets that are returned. And then I'm actually going to save the asset ID, that asset ID or asset hash. I'm actually going to save that locally, so that way we can use it for the next script that we're going to go over. And then we're just printing out the asset ID, the ownership field, and the compression field. And that'll become important here in a moment. And then we're doing the same thing again at the very end, just to demonstrate. We're getting the assets owned by our user address, and then we're just going to log out the same information. And in this case, we're actually just going to filter all these out for only the assets that are part of the same tree, because for this example, this tree, there's only one tree in this collection, so we're just going to filter that out and only log that information. And then I'm actually saving that user asset ID locally as well, because we're going to use them in the next script. Okay, so the script has completed. You can see that it's logged out two things. We have the asset ID of 3SOW, delegated to Nick, owned by 3AD, and this is the test wallet. You can see the compression information. Yeah, actually, I think I misspoke earlier. I said the asset hash is the same thing as the asset ID. That's not true. You can see right here, the asset ID and asset hash are actually different. Those are different pieces of information. The asset ID is the important piece that we will actually need. They are just different. And then you can see here we're getting the assets owned by this address, the Nick address, different asset ID, different owner, no delegate, different hash information, same tree. So that's the important thing is we have these two asset IDs, and now we can actually transfer ownership. So I'll go ahead and close these, and I'll open this transfer NFT script. So standard thing here at the top, we're loading in all of our SDK functions and whatnot, our helper functions from within this repo, our wrapper connection, making our connection to the RPC using the wrapper connection class. We're getting our test wallet and payer address, and then we're getting our asset IDs that I just showed that are all stored locally, and then we get down here. In this case, we're going to make another asset. We're going to make another RPC call to the get asset endpoint, giving it the asset ID of in this case, this is the user asset. So initially what the script is going to do is we're going to show transferring from the asset that is owned by the user, and we're going to transfer that to the test account, the test wallet. And then because that's owned by the user, and then we'll run it again to show that a delegate can also transfer that NFT as well. So we're going to get the asset information from the RPC provider, from our indexer. We're going to log it out just for sake of demonstration. And then some quick questions of, is it compressed, the owner and the delegate, the current owner and delegate? And then if it's not compressed, we're just going to kill the script, because this is only the way you transfer ownership of a compressed NFT and the way you transfer ownership of a traditional non-compressed NFT are very different. So this will only work for compressed NFTs. And now that we have our asset and we log that out just for the sake of logging it, you don't actually need to do this when you are trying to transfer an NFT. This is just for the sake of demonstration, showing the information that you get back from this RPC endpoint. But the thing you do need to do is you need the proof. So like we talked about at the beginning, the Merkle tree, if you're making a change to your on-chain Merkle tree, that concurrent Merkle tree that we created, part of the account compression program, you need the proof that is kind of like a list of addresses in order to rederive and recompute that root hash. So you can kind of think of it like if you can kind of think of the proof as like you need to prove that you know the current state before you can change the state, if that makes sense. So you have to actually provide this proof with your transaction, and that's what the canopy comes into. And we'll show how that kind of factors in here in a moment. So we're going to fetch our asset proof information from the RPC, and we're going to log it out to show the information that gets returned. And then we'll talk about how to actually like kind of parse it out and what information you really need. Excuse me. And then we're going to use the concurrent Merkle tree account class that's within the account compression program, and we're going to actually get our tree information from the blockchain. All this information is stored on chain. In this particular demo, we would have this because we just created the collection. But if you are doing, say, you're working with a wallet or something, or an exchange or a marketplace, you wouldn't necessarily have that information, but you can always fetch it from the blockchain itself, because there's some particular piece of information that we need in order to actually transfer. All right. Let's see. So the next part of this is we're actually going to take some of that information, and in this case, we're going to just locally, like client side in our TypeScript here, we're going to locally verify that the proof that the RPC gave us is valid and will allow us to actually transfer our NFT. And then there's another quick check here that says, hey, is the proof that we gave, is the information we got from the RPC the same information that is the current saved state of our tree? This doesn't really matter at all, because of the concurrency that we have with our max buffer size when we created our tree. That's like the special sauce of concurrent Merkle trees. This doesn't really matter. It's just for sake of demonstration. Let's see. So from our asset proof itself, we're getting the leaf and our root value, and then we're going to convert those to a buffer, because these are just, it's just a value that's base 58 encoded. So we can just kind of use the public key function in class to actually kind of convert it to a buffer. It's just like a helper function in a way. And then we're going to compute our proof, that is all the proof values that are given to us from the RPC. And once we actually run the script, you'll see what that looks like. And then from our on-chain information, we're getting our current root value, which is the value that's like that single piece of value that's actually like stored on chain. We're just going to get that so that way we can compare it. You don't need to specifically do any of this client-side verification unless you're trying to add like additional error handling within your local application. This proof verification is all handled by the Bubblegum and the account compression program. So you don't have to do it, and you can trust that it is in fact still secured by the blockchain. And that's kind of what this talks about, this comment block. So the proof that the RPC gives you must be a valid proof that is stored within that buffer size. In our case, I think it was like 64, because we can process 64 changes within the same block of our single tree. And so as long as the proof that you got is within that last 64, within that last buffer size amount, you can still change, that proof is still valid. All right. So the next portion here, scroll up. So the next portion here is we're actually going to build our instruction to actually transfer ownership of the NFT, of our compressed NFT. In this case, we're going to set our new leaf owner as our test wallet. So for this demo, we're transferring from the user account to the test wallet account. And then we're getting our leaf owner. This is again taken from our asset, or from the asset that we actually get from the blockchain itself. And then we're getting our leaf delegate. The leaf delegate value, just like when you minted the compressed NFT, you have to give a value. If your leaf delegate is set, that's what this is doing. It's checking if we have a leaf delegate set. If it's set, it's going to use that leaf delegate. If it's not set, you need to make sure that it's the owner, because there's no delegate, because you still have to provide an account based off how this the bubblegum instruction is structured. And then we're going to get our tree authority and canopy depth just from the information that's stored on chain. Again, in theory, we would have this with this demo, but this just demonstrates how to actually refetch that from the blockchain itself. And then there's our proof. I just happen to call it proof path. But so our proof is, like we talked about, or like I talked about a couple of times, is your NFT proof, your compressed NFT proof that you have to provide for every single transaction that alters the state, whether that's transferring ownership or updating the metadata or any other update instruction. You have to provide this proof. And this is really where the canopy depth comes into play. Because this proof is each of these individual proof values that you have to provide, it's an array. Each of these is you can kind of think of them like an additional public key address that you have to provide within a transaction. Because with Solana, like we talked about earlier, with Solana, you have to provide every single account address that is touched within your transaction, whether that's a read or a write. You have to provide all those, right? So our proof is kind of like an address. You can kind of think of it like that. It won't resolve to like an on-chain account, but it's structurally the same. So that's why we're converting this back to a public key, our node value in this case. These are all the proof strings that are provided back from the RPC via that get asset proof endpoint. And then we're just kind of massaging these into a valid account metadata array that we can actually provide with our instruction. And this last part is we're going to like truncate we're gonna chop off the end of our proof based off our canopy depth. So like we talked about earlier, the canopy depth is going to determine how much of your proof is stored on chain. This is like one of the super important parts to understand as a developer when you're dealing with compressed NFTs, especially when you are creating compressed NFTs or any other state compression trees, is because your canopy depth determines how many additional accounts you have to send with your transaction, every transaction. Having a higher canopy depth makes it so you can send less data within your transaction. Having the inverse is also true. Having a lower canopy depth requires extra data to be sent within your transaction. And because of the data size, the transaction size limits within Solana itself, you could potentially limit composability of your particular NFT collection, your compressed NFT collection, because you have to provide these proof account keys, if you will, every single transaction. So that's why the canopy depth is super important to understand at first and set correctly at first. It's a strong factor into the composability of your collection. Now, you may be thinking, you might not really care. You're just trying to create NFTs. Okay, great. Think about your users, or if you're a marketplace that's trying to handle the ability to sell your compressed NFTs, to put bids on them. Anytime you're trying to do that, the marketplace contract or an exchange type contract, they also have to provide all of these pieces of proof information, these account keys. They have to provide this as well. So if your canopy depth is too low, which means you're going to have to send a lot more data within every transaction, your compressed NFT collection might not be able to be supported by wallets or by marketplaces. Those are like kind of the big ones. So right now, so you can kind of think of it is if you set your canopy depth to your max depth -3, so you're going to provide 3 additional account addresses to every single transaction. That's basically the exact same as the traditional uncompressed NFTs, you're providing 3 additional accounts. So if you're unsure, I would recommend just do a max depth -3, and that way it's basically the exact same level of composability that a traditional NFT would have. All right. Excuse me. So now we'll actually create our transfer instruction. Now that we have all this information already computed and set, we can just create a transfer instruction very quickly, just like you would any other instruction. You're using probably a helper function from an SDK. You're providing in some of the account addresses. We've got our tree authority, owner and delegate, new owner, and then we're providing the program addresses that we have to interact with. And then we're providing our proof path with this particular function, because we're dealing with compressed NFTs and state compression. We're going to provide our proof path within this instruction. And then we have to provide the other information that's required by the account compression and the bubblegum program to actually verify our proof on chain. We're going to take the root that is given to us by the RPC provider. We're going to send that. In this case, you can kind of see this like, if you're not super into JavaScript or TypeScript programming, I'm basically just massaging this information into an array of numbers, because if I hover over this helper function that's provided by the JavaScript or the bubblegum SDK, it requires a list of array of numbers. So I'm kind of just massaging that into that format. But we're sending the root, the data hash, and the creator hash that are all given to us from the RPC indexer itself. And then we're giving the nonce index value that is our current leaf ID. And then finally, our bubblegum program, since this is all owned by the bubblegum program. And we're going to take that transaction, or we're going to take that instruction, slap it in a transaction, sign it, send it to the cluster, and we're going to print out the Explorer URL. And then also, for the sake of demonstration, I am refetching that asset, and then just to display that our ownership values have changed. So our old owner and old delegate will actually update to our new owner and delegate. And then something to note here is that if your owner changes, then your delegate will also reset. So like for the second NFT that we minted to the test wallet for this demo, it's owned by the test wallet, but it's delegated to the user because that's just how we set it up. So if we transfer that NFT, the delegate will reset automatically, and that's just handled by the bubblegum program. So that's very nice of them for us. All right. So now with all that precursor information, we will actually transfer our NFT. So we'll run our transfer NFT script, and it's gonna, do all the things we talked about, make the connection to the cluster. It's gonna fetch all that asset data, the asset proof. It's gonna log it out to the console just to demonstrate what it looks like, and then it's going to send our transaction, which it sent it super quickly. So I'll just scroll back up here to the top of this. So you can see we are getting our payer address, that's that NIC value, the test wallet address, the 3AD, and then our 2 asset IDs that we showed in the last script when we're fetching that from the provider. And then we're logging out the entire asset, similar to what we showed earlier. We have all the data that gets returned. And then we're checking, is this a compressed NFT? Yes, then we're good. The current owner is this NIC value, and the current delegate is null because there's no current delegate set. And then we're actually fetching our asset proof. You can see here, this proof value just returns a string, or an array of strings. And like I mentioned, is you're looking at these and you might think that, hey, that looks a lot like an account address that you would just be able to pop into an Explorer and see the information. Well, that's not necessarily true, because these are not actually account addresses. This is just the information that is stored within the Merkle tree, and this is kind of like, you can almost think of it like an address within the Merkle tree. So you won't be able to actually just pull this up in a block explorer to see the values, but we have this large list. So if you count all these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We have 17 proof values that are submitted with this, that are returned from this, and that's our entire proof if we're going to make our change transaction, so our transfer NFT or update metadata, we have to provide this entire proof. That's a lot of data to send within a single transaction, right? And that's where the canopy comes in. The canopy allows us to chop off those last, five or so that we have for our example. We're chopping off those last values, significantly reducing the amount of data that we have to actually send with our transaction. So it cuts down on the transaction bite size quite a bit. And then we're just checking that quick client-side verification of, is our proof valid? In this case, it is true, so that's good to see. And the current value does match because this was the last NFT that we minted. So the current root matches this root because it was the last one minted. And you'll see that pretty common. If we go to transfer any other NFT, more than likely that will no longer match because the providers, the indexers, are really only going to update it every buffer size worth of transactions. If you can kind of think of it like that. All right, so we set the transaction. It completed successfully, and I will even throw this in the chat if anyone wants to look at it. And you can see our old owner was Nick, our new owner's Nick. So we basically sent it back to ourselves and paid a small fee, just because how this script is actually set up. But now that we have fully walked through it, I will update it to show that we are going to, where is it? Here it is. So now we'll run this script again, and we're going to transfer our our asset that's owned by the test wallet, which is delegated to our user wallet. The user is signing this transaction, so the user is able to they have delegated authority over this particular NFT, so the user can actually transfer it and handle that. So we're going to do the exact same thing, except we're going to transfer the test wallet owned asset to the user now. So we'll go ahead and run the script again, and we'll be able to see that. And the transfer goes through successfully. And you can see our old owner was this 3AD. The old delegate was Nick, so Nick was delegated. And then Nick transferred because this Nick account signed the transaction because it was delegated authority, it could in fact transfer this asset to the user because that's where we're transferring it to. And then because we actually handled this transfer instruction, the blockchain handled it, it resets the delegate because we no longer have a delegate because we performed a transfer transaction, or a transfer instruction rather. So now we can use our script that we showed earlier, and we can go ahead and fetch our assets by the owner, and we can show the current ownership state of those NFTs. So we just got the same two assets, and you can see that both of these assets are now owned by that 3AD address because we transferred ownership to them. And you can see asset ID is now owned by 3AD, and these are the two same asset IDs. Now, just for demonstration purposes, and this will be the last thing I actually show, is we can try to transfer the NFT again, and we'll see that because this user address is no longer delegated, the transaction will fail because you don't have authority, and this is the only account that's actually signing the transaction. And then I'll also pull it up give the link in the Explorer, so you can see our transaction failed. And if you can pull it up on the Explorer, and you can kind of see how this type of failure will look within the program logs. So I'll go ahead and switch over the stream to show that. And like I said, this will be the last thing we end up going through. zoom in a little bit. So you can see that our transaction, this particular transaction, this transfer, it did fail. There was an instruction error from the program, and only this single fee payer signed the transaction. There was no other signatures, and that it failed because this address is no longer delegated authority. You can kind of look through the information that's in here. It's, you've got your various tree information. You have our remaining accounts that we're sending, and those are the values that you can see in our proof. And then if you look at the logs, say there was an error, the leaf authority multi-signed, and this transaction must be signed by either the leaf owner or the leaf delegate. So you can kind of see that just kind of how the errors will be structured for bubblegum program errors. And then they're pretty reasonable. You can pretty easily and pretty quickly figure out what's going on and what happened with your transaction, and then troubleshoot accordingly. So that is the last of it. Can I do 1080p and increase the font? Are you talking about for the instruction, or for the Explorer? Is that your question, Shershak? I put the link directly inside of the chat, so you can just open the Explorer link yourself and also browse it, just to make it a little bit easier. I can't really zoom in a whole lot further, or change the resolution. If anyone has any last minute questions, you can go ahead and put them in the chat, and I'll try to answer them. We'll probably do another 5 minutes or so if people do have questions, and if there's no questions, then we'll wrap up this live stream. And I hope everyone who stuck around for the whole time or joined any portion of this, I hope you learned something about compressed NFTs and kind of how to interact with them and mint them and whatnot. I can't wait to see what all gets built with compressed NFTs and state compression on Solana. It's going to be awesome. All right, so it doesn't look like there's any questions. So thanks everyone for joining, and keep an eye out for further documentation and examples and whatnot for compressed NFTs. And there's a couple of questions about, is the stream recorded? It is recorded. I'm not sure the timeline for publishing the pre-recorded version. But if you just make sure you keep an eye out on the Solana Developer's Twitter, and once that content does actually get published live elsewhere, probably on the Solana Foundation YouTube, then we will announce it there. So I guess we'll go ahead and wrap this up. Thanks everyone for watching. Hope you have a good day.